So I have here a large magnet, South Pole, North Pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. Get this guy out of the way. And there you see it, floating there. Because now that I've reversed the direction of the current is flowing this way, magnetic field is pointing up, we expect an outward force. And that's what you say. Right-hand rule, simplified.
All right, so no current. The magnetic field is coming out of the page here. As soon as you run a current in the upward direction, notice that the wire gets deflected to the right. And then if you reverse the direction of the current, the magnetic field is gonna, the wire is gonna get deflected to the left. All right, so the current goes up, deflection is to the right, current is coming down, the deflection is to the left. So what's causing that to happen? Oh, you got this positive charge moving in this direction. This is your velocity vector. This is your magnetic field. All right, this one is a vector, so is this one. So it's gonna experience a force in this direction. So this is Q. This force is going to be 90 degrees to motion itself, and there's an angle between the magnetic field and the velocity vector. So this magnetic force, by definition, is this charge moving at the speed cross B, which can otherwise be expressed in terms of QVB times the sine of the angle in between. All right, so this is the right-hand rule, number 1, for a single charge particle. All right, so right-hand rule number 1 for a single charge particle looks like that. Okay, so the same thing is gonna work for our current. Now, instead of a single charge, you have a current moving in this direction. So a number of charges are moving in this direction, so it causes a current along the length of this wire. All right, so this is along the length of this wire. You got the magnetic field moving in this direction, so this thing is going to experience a force in the opposite direction. So you got the current along the length of the wire across B, so this is going to give you the strength of the magnetic force acting on it. All right, put differently, it looks like this.
Wait, but this is for a positive charge, right?
Okay, hold that thought. All right, so it's going to be ILB times the sine of the angle in between. All right, so it's the same. This is the right-hand rule number 1, and this is the application of the right-hand rule number 1 for our current. Okay, so both of them are the same things. All right, right-hand rule is always used for a positive charge. It's always used for a positive charge. If it's a negative charge, you have to use the left hand. In classical physics, underlying assumption is the positive charges are the ones which are moving, not the negative charges. It's going to be related to torque. All right, a couple of things. Just find this first from the handout and get to this page. I'm gonna skip the details. I'm not interested in derivation, but there are a couple of things that I'm interested in. Number one, I want you to notice that this one is gonna be a current loop. All right, so you have a wire, the current loop, which is gonna be placed inside a magnetic field of some sort. So the magnetic field is pointing in this direction. So you got the loop, the current loop, and the magnetic field is gonna be inside. And I want you to acknowledge the fact that this loop is going to experience some kind of a torque. All right, so this expression says this loop is going to experience a torque. So the question is, why will the loop experience a torque? All right, so let's figure that out. The loop is going to experience a torque. If you have a current loop inside a magnetic field, what it's going to do is it's going to experience a magnetic torque. So the question is why. All right, so notice that the magnetic field is pointing in the downward direction. So this is your magnetic field pointing in the downward direction. And there's a current moving along this direction. All right, so the current is moving in this direction, and the magnetic field is moving in the downward direction. All right, so cross product is what you need to use. Your thumb is gonna be lined up in the direction of the current. Magnetic field is pointing in the downward direction, so this thing is gonna experience a force to the right. So this thing is gonna experience a force to the right. All right, so the force is in this direction, which means that this thing is gonna snap in this. It's going to snap in this direction. So this is going to snap. It's going to experience a force in this direction. It's going to experience a torque in that direction. All right, so it's going to experience a torque in that direction. You guys are looking at a speaker. You got the cone, you got the voice coil over here. And notice that you got a permanent magnet. The coil is going to go into the permanent magnet. And I want you to notice that this represents. All right, here the current is coming out of the page. All right, so all right, here the current is coming out of the page. Here the current is going into the page. When that's the case, notice that there's going to be a force of deflection in this direction. If you reverse the direction of the current, the force is also going to reverse direction, right? All right. If the voice that it's trying to capture has a frequency of 500 hertz, which is 500 cycles per second, what that means that the current is going to reverse direction 500 times per second. As a result, the cone is going to vibrate back and forth 500 times per second. So if you reverse the direction of the coil, if you reverse the direction of the current, the force is going to reverse itself. All right, so those are just the examples of it. All right, so electric motor is the one that we're going to talk about. All right, so notice that you have a current loop. It's a coil in this case. You got multiple turns on it. And then you have a magnet. Magnet is generating a magnetic field moving in the opposite direction. So the coil is intercepting that magnetic field. And then when you start to spin the coil, it's going to keep on spinning, which means that it's experiencing a torque. So the question is, why is it experiencing a torque? What's causing the torque on the coil?
So you create yourself an electric motor as a result. So number one, you have to have a current going through the wire. And when you place a magnet inside it, that current is going to experience a magnetic force. And then the magnetic force is going to be responsible for the torque acting on it.
Didn't he also have to scrape off the insulation on the
Right.
inside of the wire so that the current turns on and off?
All right, let's just ignore that comment right now, just briefly. We'll get back to the details later. All right, guys, in this case, the current is going up and then turning around and coming back down. What I want you guys to do is I want you to focus on this segment of the current. Notice that the current is going up. Line up your thumb in the direction of the current. Line up your fingers in the direction of the magnetic field. When you line up your thumb in the direction of the current and the fingers on the direction of the magnetic field, you will notice that this thing is going to experience a force into the page. It looks like this. All right. So here the current is going into the page. Here the current is coming out of the page. So your thumb is going to be coming out of the page. Your fingers are lined up in this direction. And notice that the segment experiences a force. And this force is going to cause a rotation with respect to the center, to the pivot point that you're looking at. All right, so the magnetic force is responsible for the torque that you're looking at. Now, instead of